Now let's move on to the next topic of our chapter, the empty set. Let us consider the set A, set of all x such that x is a student of class 11 presently studying in a school. This set describes the set of students presently studying in class 11 of a school. The students of a class are easily countable, so we can say that this set consists of a fixed or a finite number of elements. Now let us consider another set B, set of all x such that x is a student presently studying in both classes 10 and 11. That does not make sense, right? A student cannot study in both the classes 10 and 11 at the same time. So we can say that this set contains no element at all. And what do you call a set which contains no element? A set which does not contain any element is called the empty set or the null set or the void set. From this definition, we can say that set B is an empty set and set A is not an empty set. An empty set is denoted by the symbol phi or curly braces. Now let's take a look at some sets and determine whether they are empty or non-empty sets. First set, A equal to set of all x such that 1 less than x less than 2 and x is a natural number. It's given that x lies between 1 and 2 and also x is a natural number. How is that possible? We know that there lies no natural number between 1 and 2. So we can say that set A is an empty set. Our next set is B equal to set of all x such that x square minus 2 equal to 0 and x is rational number. Here it's given that x square minus 2 equal to 0 and x is a rational number. What is a rational number? A rational number is of the form p by q, where q not equal to 0 and both p and q are integers. Any integer can be represented in the form of a rational number, like minus 2 by 1, minus 1 by 1, 1 by 1, 2 by 1, etc. In the equation x square minus 2 equal to 0, for LHS to be equal to RHS, the value of x square must be 2. But on substituting these rational numbers in the equation, we can see that none of them satisfies the condition. So we can say that this set is an empty set. Let's take a look at another set. C equal to set of all x such that x is an even prime number greater than 2. Here it's given that x is an even prime number greater than 2. Let's take a look at the list of prime numbers from 1 to 100. Here we can see that 2 is the only even prime number. So there does not exist any even prime number greater than 2. Therefore, it's safe to say that set C is an empty set. The next set is D is equal to set of all x such that x square is equal to 4 and x is odd. Here the condition given is x square is equal to 4 and x is odd. We know that 2 square is equal to 4 and 2 is an even number. So the equation cannot be satisfied by any odd value of x. So we can say that this set is an empty set. And that was the concept of an empty set. Now let's move on to the next topic, finite and infinite sets. A set which is empty or consists of a definite number of elements is called finite. That is, in finite sets, the number of elements are fixed or can be counted. For example, the set of all the days in a week is a finite set as the number of elements are fixed. The next example is the set of solutions of the equation x square minus 16 equal to 0 is a finite set. Let's see. The equation here is x square minus 16 equal to 0. We can write this as x square is equal to 16. So x is equal to root 16. Then we get x equal to plus or minus 4. So the solutions of the equation are x equal to minus 4 or 4 and can be written as S equal to set of minus 4, 4. As you can see, this set has finite number of elements and is a finite set. The next type of set is non-empty finite set. Number of distinct elements of a set, for example, of set S can be denoted by n of s. So if the number of elements n of s of set S is a natural number, then S is a non-empty finite set. Let's take a look at an example. A equal to set of 1, 2, 3, 4, 5. Here set A has 5 elements, that is n of A is equal to 5, which is a natural number. So we can say that A is a non-empty finite set. The next type of set is infinite set. A set which is not finite or does not have a definite number of elements is called infinite set. For example, the set of all natural numbers is an infinite set as there is no limit to the elements of the set. As you can see, when we write a set in roster form, we list out all the elements of that set within braces. But it is not possible to do so in the case of infinite set, as the number of elements would go on, and it is not practical to do so. So what we do is, we represent it by writing the first few elements followed by 3 dots. The set of odd natural numbers, the set of integers are some of the examples of infinite sets. But all infinite sets cannot be written in roster form. For example, the set of all real numbers cannot be written in roster form because the elements of this set do not follow any particular pattern. Now, let's solve some examples for better understanding. State which of the following sets are finite or infinite. The first set is set of all x such that x belongs to n and x minus 1 into x minus 2 is equal to 0. Here, the set is given in set builder form and we have to find out if the given set is finite or infinite. First, let's solve the equation x minus 1 into x minus 2 equal to 0. Here, x minus 1 equal to 0 and x minus 2 equal to 0. So, the values of x are 1 and 2. So, we can write the solution set of this equation as set of 1, 2. As you can see, the elements of the set are finite. So, this is a finite set. The next one is set of all x such that x belongs to n and x square is equal to 4. Similar to the first one, let us solve the equation here. Here, x square is equal to 4. So, x is equal to root 4. That is, x is equal to plus or minus 2. So, the values of x are minus 2 and plus 2. Now that we have the elements, let's write this in roster form. We get set of minus 2, 2. And we can see that the elements are finite here. So, we can say that this is a finite set. Now, let's move on to the third one. Set of all x such that x belongs to n and 2x minus 1 is equal to 0. The equation here is 2x minus 1 equal to 0. So, we can write 2x equal to 1 and x equal to 1 by 2. But it's given that x belongs to n and the value of x here is 1 by 2, which is a rational number. So, we can say that this set has no elements at all and is an empty set. And we know that an empty set is also a finite set. Now, let's move on to the next set. Set of all x such that x belongs to n and x is prime. Here, the condition given is x belongs to the set of natural numbers and x is a prime number. So the given set is a set of all prime numbers which is infinite. So this set is an infinite set. Now let's take a look at the next set. Set of all x such that x belongs to n and x is odd. Similar to the last one, the condition given here is x belongs to the set of natural numbers and x is odd. So we can say that this set is a set of all odd numbers and is infinite. So this is an infinite set. Now let's move on to the next topic. Equal sets. Two sets A and B are said to be equal if they have exactly the same elements, and we write A equal to B. Otherwise, they are said to be unequal and we write A not equal to B. Let's take a look at an example. Consider two sets A, set of 1, 2, 3, 4 and B, set of 3, 1, 4, 2. Here we can see that both A and B have the same elements. So we can say that A is equal to B. Now let's take a look at another example. Let A be the set of prime numbers less than 6 and B be the set of prime factors of 30. So what are the prime numbers less than 6? They are 2, 3 and 5. That is, A is equal to set of 2, 3 and 5. And what are the prime factors of 30? They are also 2, 3 and 5. So B is equal to set of 2, 3 and 5. So here we can see that both A and B have the exact same elements. So we can write A is equal to B. Now let's take a look at another example. Consider the sets A equal to set of 1, 2 and 3 and B equal to set of 2, 2, 1, 3 and 3. These two sets are equal. Can you tell me how? We can see that both the sets have the same elements 1, 2 and 3. But in set B, element 2 and 3 have been repeated. But does it make any difference? No. In a set, an element can be repeated multiple times, but it is counted only once. So here we can write A is equal to B. Now let's take a look at some examples. First one, find the pairs of equal sets, if any, give reasons. A equal to set 0, B equal to set of all x such that x greater than 15 and x less than 5, C equal to set of all x such that x minus 5 equal to 0, D equal to set of all x such that x square is equal to 25, and E is equal to set of all x such that x is an integral positive root of the equation x square minus 2x minus 15 equal to 0. So here we are given a couple of sets and we have to find out the pairs of equal sets. So here the first set is A and its element is given, that is 0. The second set is B. Here the conditions given are x is greater than 15 and x is less than 5. So when x is greater than 15, it implies the values of x could be 16, 17, 18, etc. That is, any value greater than 15. And when x is less than 5, it implies the value of x could be 4, 3, 2, etc. That is, any value less than 5. So it's safe to say that there does not exist any value that can satisfy both the conditions. So we can say that B is an empty set. The next set is C. The condition here is x minus 5 is equal to 0. Solving this equation, we get x is equal to 5. So the set C has only one element and it is 5. The fourth set is D. Here the condition is x square is equal to 25. Let us solve this equation. So we can write x is equal to root 25. Then we get x is equal to plus or minus 5. So the values of x are minus 5 and 5. So set D has two elements and we can write D is equal to minus 5, 5. The next set is E and the condition is x is an integral positive root of the equation x square minus 2x minus 15 equal to 0. This equation is of the form ax square plus bx plus c equal to 0, where a is equal to 1, b is equal to minus 2 and c is equal to minus 15. So the element of the set is the positive root of this quadratic equation. Let us solve this equation using the quadratic formula, that is minus b plus or minus root of b square minus 4ac by 2a. On substituting the values, we get minus of minus 2 plus or minus root of minus 2 square minus 4 into 1 into minus 15 by 2 into 1. Simplifying this, we get x is equal to 2 plus or minus root 4 plus 60 by 2. On adding the terms inside the root, it becomes 64. We know that root 64 is equal to 8. Then our equation becomes x is equal to 2 plus or minus 8 by 2. So the roots are x is equal to 2 plus 8 by 2, or x is equal to 2 minus 8 by 2. That is, x is equal to 10 by 2, which is equal to 5, or x is equal to minus 6 by 2, which is equal to minus 3. But in the condition given, x is an integral positive root. So we can only take the positive root out of these two. That is, x is equal to 5. Therefore, E has only one element, and that is 5. Now let's compare each set and find out the equal pair. On comparing, we can see that out of 5 sets, only 2 form a pair of equal sets. That is, C and E both have the same elements. Now let's move on to the next example. Which of the following pairs of sets are equal? Justify your answer. First one, X, the set of letters in alloy, and B, the set of letters in loyal. Here, X is the set of letters in the word alloy. That is, X is equal to set of A, L, O and Y, and B is the set of letters in the word loyal. That is, B is equal to L, O, Y and A. On comparison, we can see that both the sets have the exact same elements. So we can write X is equal to B. The next one is A equal to set of all n such that n belongs to the set of integers and n square less than or equal to 4, and B equal to set of all x such that x belongs to R and x square minus 3x plus 2 is equal to 0. Let us take the set A here first. We can see that the condition given here is n belongs to the set of integers and the square of n is less than or equal to 4. So, in the set of integers, what are those numbers whose squares are less than or equal to 4? They are minus 2, minus 1, 0, 1 and 2. So we can write A is equal to set of minus 2, minus 1, 0, 1 and 2. Now let's take a look at the next set B. Here the condition given is x belongs to the set of all real numbers and x square minus 3x plus 2 is equal to 0. Here we can see that this equation is a quadratic equation. where A is equal to 1, B is equal to -3 and C is equal to 2. So we can solve this using the quadratic formula. That is, x is equal to minus b plus or minus root of b square minus 4ac by 2a. On substituting the values, we get x is equal to minus of -3 plus or minus root of -3 square minus 4 into 1 into 2 by 2 into 1. On simplifying, we get x is equal to 3 plus or minus root of 9 minus 8 by 2. Here 9 minus 8 is equal to 1. Then our equation becomes x is equal to 3 plus or minus root 1 by 2. The value of root 1 is 1. Then we get x is equal to 3 plus or minus 1 by 2. So we can write x is equal to 3 plus 1 by 2 or x is equal to 3 minus 1 by 2. That is, x is equal to 4 by 2, which is equal to 2, or x is equal to 2 by 2, which is equal to 1. So we can write B is equal to set of 1, 2. Therefore, the two sets are A is equal to set of -2, -1, 0, 1 and 2, and B is equal to set of 1, 2. We can see that the elements differ in both the sets. So we can say that A and B are not equal sets.